Hi, welcome back. Previously, we had been talking about motivation for understanding diffusion from a biophysical perspective, but applied to what is critical to all of human life and physiology, namely diffusion of gases for respiration and ions for nerve transmission. We then went on to talk a little bit about how fast proteins diffuse inside cells, and it is an underappreciated mechanism by which transport can occur. We then went on to speak very briefly about the fact that even cells themselves, small cells like E. coli, can undergo random walks, which is itself a hallmark of diffusion, a kind of nature of diffusion. And in fact, you will find that the mathematics of diffusion statistics, or what are called random walk statistics, have wide applications. So in a way, it's a standard model that if you understand once, you might even be able to have some fun. I don't know whether you'll make a profit at the stock market. I talked very briefly about Einstein's papers 1905 to 1908, which form the foundation of many of the physical theory or the mathematical reasoning that came out of that period of work of his and of a few other people, including Smoluchowski, and I will elaborate on that a little later. Finally, we ended with this idea that microscopic thermodynamic theory gives us a basis for diffusion in terms of the root mean square velocity, which is under root v x square. Those angled brackets simply indicate average, is equal to kBT by m. Now, I didn't show you the solution, so I am telling you the answer already, that if you take lysozyme, which has 129 amino acids and 14.33 kilodalton molecular weight, molecular mass in Dalton units, then the v root mean square velocity in one dimension of such a lysozyme molecule is 1.32 into 10 to the power 3 centimeters per second. Now, this is just a number and you can argue about it, but just think about it like this: it is moving roughly 1000 centimeters in 1 second. That is about 10 meters per second. 10 meters per second is so fast that if you had wave of 10 meters per second coming at you, you would call it an explosion. You understand that. So, since that is not happening, I am standing here, there is no explosion going on. I know lysozyme molecules are not diffusing, but all the other air molecules are diffusing, even if they are smaller. In fact, it turns out that kBT by m indicates that smaller mass means higher velocity, right? I mean, so even faster motion is possible, but we don't see that. We don't see explosions around us in the air. So, what's going on? So, this is the reason why the physicists who pioneered the study of diffusion came up with random walk theory, and this is what we are going to talk about today, because nothing happens in vacuum. All these assumptions of RMS velocity are based on vacuum assumptions and in the absence of any collisions. We know that in a solution, and in fact in any fluid like air, yes, air is a fluid, one can prove experimentally that molecules are undergoing collisions, constant collisions, and changing direction all the time. So, even though the instantaneous very tiny minuscule velocity is very high of tens of meters per second, the net velocity, the net movement is very minuscule, and we will see from random walk statistics how to make sense of this. So, today I am going to talk to you about random walk in terms of 1D, propositions of a random walk in terms of its average displacement and extent of speed, and I will stop there and we will continue with diffusion and in terms of diffusion time, or time it takes to diffuse, and velocity of diffusion. Okay. So, what is a one dimensional random walk? Now, I am going to do a little poor man's experiment. This is an ink pen, and you can see that I have a glass of water. It's is it drinkable? So, this is drinking water, and I am going to spoil my drinking water by putting a drop of ink in it. Now, all of you potentially know the answer to this question, but I want to demonstrate it because it is something that is, as I keep reminding you, there are some experiments that are quite cheap to do, and you can do them and test them, because science is all about testing our curiosity. I do not mean kill an ant and find out if it is dead, that is obvious. These are slightly more sophisticated thoughts, right? Simple experiments means experiments that are simple in implementation but sophisticated in concept. So, here I drop, let us see if this ink comes out. There it is. Okay. So, what you should see is a cloud of ink in the center of my glass, and what you should see is I am not touching it, I am not moving it, but it is moving by itself, right. What is this motion due to? And that is the foundational question that diffusion theory attempts to answer. Because one of the things you also see, along with the fact that it has gone to the bottom, probably because ink is more viscous a material than the water itself, it is water based ink though. Eventually, after we finish this module of the lecture, we will look at it and ask the question, what happened to the position of the ink? Is it all still in one place? Is it moved? Has it gone up a gradient, down a gradient? What happened? Okay. So, in that spirit, we will continue back with our theory and we will return to this glass of spoilt water, which I will not drink after this, and see what happens. Okay. All right. So, what is a one-dimensional random walk? So, imagine we have a particle of a certain size positioned at 0 on an x axis. Yeah. Now, this particle can undergo motion by either going here or here. We call this plus delta and minus delta. And in fact, at the next step, this particle may choose to go, can I move this? Yeah, okay. May choose to go right or left. So, I do not want to change the size. So, it may go right or it may go left. So, return to its original position. And this hopping from left to right and right to left is random. This is partly why the nature of that term originates, that it is a random walk, right, because there is no guiding principle, there is no other influence in such a conceptual pure random walk. And you should go back and look at physical chemistry textbooks. Atkins is a standard reference in the field, to ask the question, why is there no direction? Why should there be? Why is up, down, left, right, forward, backward, they are all equal? Why? Why? Okay. And you may stumble across a principle which you may have come across earlier also in chemistry and physics, which is the Equi-partition theorem, and I will not dwell on that because that is not the focus of today's lecture, but please go back and look, right. So, for our purposes, we define time as t and position as x, because remember this is one dimensional. We are simplifying. Remember, this is another fundamental principle in physics that we are applying to biology, which is we may have a very complex cow, we simplify it to a sphere. We want to know the typical size of a cow, so we take its radius, because these are simplifications. Does it mean that a cow is a sphere? Obviously not. But this is important because simplification allows us to think, allows us to intuit. Okay. So, simplification of our system in one dimension for all particles at t is equal to 0, x is equal to 0 is the initial position, and we have rules of motion. These rules are what constitute the random walk model. This is a conceptual theoretical model, and we will see in the later segments of this module where the rules actually show up in real life in terms of biology also. So, each particle can go left or right in steps of delta, that is the symbol here that you see, delta, and the time that it does each of these steps is referred to as tau. As you remember, delta and tau are symbols used to represent very small, infinitesimally small steps in space and time, right. So, then the distance is in fact is equal to delta is equal to plus or minus V x times tau, because we have now added another term which is V x, which is the x velocity, one dimensional velocity, which then allows us to say that the distance is nothing but the product of time and velocity, right. And so, since we have defined that tau and delta are both constant, we need to answer the question, what decides these constants? I mean, is it universal for every particle? No. The idea is that tau and delta are both capable of depending on particle size, structure of the liquid, meaning viscosity, any obstacles, whatever there is, and temperature of the system. So, in that sense, our tau and delta are going to vary if we have a big particle or a small particle, whether we have motion in water or in ethanol or in air, and so on and so forth, right. So, the second part of the rules of the random walk are that the probability is equal. That is to say, p left is equal to p right is equal to 1 by 2 or 0.5. This is nothing but the familiar problem that you have all had to deal with in statistics class, that is the problem of heads and tails, right. Every cricketer knows this, every football coach knows this, heads and tails. This is tail, the number 5 for the 5 rupee dollar coin, and this is the head, Ashoka lion, and when I toss it, if the coin is fair, I will get either tail, or I will get tail, or I will get tail, or this is a biased coin, and then I get heads. Now, this is important because in the later segments we return to this question of heads versus tails and the nature of a so called fair coin. And fair coin tossing, even if it is fair, you just saw this, right. Maybe I will repeat this. If I now start tossing just 3 tosses, 1 I get a head. I am not a magician, don't worry. Head, head, my God, I got 3 heads. How is that possible? I am not a magician, I am not playing tricks, this coin is fair, I got it from the bank. So, what is going on? And this is something interesting because statistically speaking, in terms of actual theory of numbers, these are called low number limits, and we will talk about distributions, fair coins, probabilities, and the nature of low number events, rare events in other words. And I think the word that you all remember probably is binomial distribution, and we will talk a little bit about it later segments. But for now, we will say that since the probability of left and right is equal, each individual particle must follow that rule even though it is random. Interaction with water results in the fact that the particle has no memory and each step is independent, and this is a statistical process. This is what I have been trying to say. And if you remember in your high school and college and university statistics, the definition of statistical means large numbers, correct? Large numbers. Statistics, I mean, I cannot say I go to a classroom and I do a statistics of heights of boys and girls with 3 boys and 2 girls and say, oh, the boys are taller than girls. I mean, it makes no it has no meaning. The word statistics has no meaning. Yeah, it is just anecdotes otherwise. Now, there is a detailed statistics of such experiments where numbers are themselves limiting, and this is a typical problem in cell biology and biology in general, and we will discuss it because of that reason, because in a way these are real world problems, or you may say applied statistics problems. But the word statistics implies large numbers, right. So, each particle is independent of all other particles. This is the third law. So, the first 2 laws are each particle has the ability to step left or right by a step delta and time t with a velocity vx, leading to delta is equal to plus minus vx into tau. The second rule is that there is an equal probability of left and right, and the third rule is that each particle is independent of all other particles, meaning to say when a particle is moving here, it does not influence the motion of a particle nearby or even further away. There is no action at a distance, there is no memory, there is no interaction between the particles, and these are important. So, please bear these in mind. We will return to these and use them for our derivation. So, the next thing that we want to do is make propositions, meaning to say what does the random walk imply, what things do we learn from the mathematics of random walk statistics or the model of random walk. So, remember in physics, model has a very precise meaning. You have to write down an equation, you have to write down mathematical laws that define it, and this is what makes biophysics so powerful, because we employ the laws that we have learnt in physics over 200 years, 300 years and apply them to biology in a way that we had not thought of before and test them with experiment. This is why we become quantitative biology and not just biophysics or structural biology or something like that. Okay. So, the first proposition is a very funny proposition. It says go nowhere. What does this mean? This is almost like some philosophy, right? I mean, I do not go anywhere. Who am I? Where am I? What is going on? But no, let us define it precisely. N is the number of particles, I is the particle identity, x underscore I of n is the position of the particle, and n is the step, small n is the step number. This you can see here. Capital N is the number of particles. This is the difference. Please note this. Rule 1. Okay. So, now we come to rules. Rule 1 of the random walk says that xi of n, that is to say the ith particle, let us say there are 5 particles, then the first particle in the nth step number, meaning its first step, second step, third step, fourth step, etc., will move in a way that is the sum of x I n minus 1, meaning its previous position in x, plus or minus delta. This is nothing but what we said earlier, that the particle jumps from one position to the next and it is moving either left or right depending on the exact random choice made at that instant, and that is what that plus and minus sign indicates, and delta indicates the fact that it is of a finite step size, right. Rule 2 says that the probability of plus delta is equal to 0.5 and the probability of minus delta is equal to 0.5. In other words, there are equal probabilities of left and right, and we will use these terms in a few minutes. Okay. So, the first task in this proposition, we said go nowhere, right, go nowhere, random walk goes nowhere. Those of you who are fond of reading, look up a classic textbook by on Mr. Tompkins. I will keep the list of reading, extra reading at the end. You are welcome to read it and go back. This is about a story told by George Gamow, who is the author of the book, about a drunkard who comes out of a bar. The question he asks is that when the drunkard walks out of a bar, he or she, yes, we are modern India, so everything is possible, can step out and then he or she wants to find the way home. I mean, and because they are in a state of inebriation, in a state of unable to decide where is home and where is the bar, they try to walk. They try walk left, walk right, they do not remember what happened, they stumble, and this, I mean, jokes apart, this is exactly what a random walker does, because at the end of the day there is a very good chance that the drunkard and the particle do not go anywhere, right. And so, in order to know mathematically, to come back to the science, what is the displacement in n steps, we need to consider I individual particles and take the ensemble average over all particles, because of course, we say one drunkard, okay, maybe this drunkard was really stupid, so he or she did not get home, but the third drunkard maybe gets home. So, we want to find out how many drunkards does it take to reach home, right. So, average of x I n, the averaging sign is that these angular brackets here. This is telling us that it is average over all particles whose indices go from 1 to capital N, I, from I is equal to 1 to capital N, and the small n indicates the number of steps they take, the nth step. So, that can be written as an equality of 1 by n, which is the average. So, 1 by n, capital N is equal to the summation, this sigma sign is just summation over all particles of the ith particle in the nth position and summed and averaged, right, over all particles, we said that. So, the sum of positions in time averaged over all particles should tell you how far the particles get. If we substitute 1, which was this equation, that is x I n is equal to x I n minus 1 plus or minus delta, meaning to say what is the xith value, it is the previous position plus or minus delta, right. We decided that was rule 1 in fact. So, we substitute that and put it in here, but the average of n steps, that is to say plus or minus delta, if I toss my coin and I ask, if I say heads is 1 and tails is minus 1 and I do this 100 times, the average is expected to be 0, right, because plus 1 minus 1 plus 1 minus 1 minus 1 plus 1 0, right. Since 1 by n is equal to into 1 by n, or the average over all particles of the summation of delta averaged is equal to 1. So, we can rewrite this equation just simply as x I n is equal to 1 by n this. What you notice is that I dropped out this term, correct. Now, this leaves me with the idea that x I n is equal to x I n minus 1. What does this mean? Mathematically you can see it, but what does this mean? Yeah, this means nothing but jahan the वैसे ही रहे, where it was, it stayed there. Okay, the average position of nth step is the position at n minus 1th step. That's what we mean. The position is unchanged on an average, but as you see with this glass here now, okay, remember we started with a large drop of ink in the center. What do you see now? The thing is completely blue. That is amazing. Who did it? What drove it? What is the cause of this motion? I mean, something has to move. There has to be some driving force to it, right? This is nothing but the magical effect or the physical effect of diffusion. I say magical not because it's magic, but because there's some simple physics in it. And this simple physics, if you understand it, you will also understand a lot of biology from it and biological transport. So the reason why it spread here was, and you will all have learned this, that if you have an initial position where all the particles were concentrated and you wait for a while, then it will spread, right? And that's what happened. It spread, it distributed itself uniformly in the glass of water. The colorless, what to our eyes, all wavelengths of light are transmitted by this. So it was colorless. Now suddenly it is reflecting blue. We can see blue in it, right? And that is because the ink molecules have nicely uniformly distributed. It has spread, in other words. But I just said to you in my derivation that the particle on an average does not go anywhere. So what's going on, right? We need to reconcile these two things, the physical reality that we can observe and the mathematical rules that we have just written down. So for that, we will talk about the second proposition, which is the extent of particle spread. We return to the slides again, right? So in that sense, we have to calculate something called the root mean square displacement, or RMSD, of the particle. And for that, we write down root mean squared, right? You see the signs. So the under root sign is for root, mean is the pointy brackets, and squared term of the displacement. So we want to find effectively equation 1 squared, right? We want to take this equation and square both sides. So we will do that. Okay, let's do that. So when we square it, we get this slightly larger term, xi n minus 1 plus minus delta whole squared, which we say is xi square n minus 1. You open it out just in your high school method, plus minus 2 xi n minus 1 delta and plus delta square. RMS displacement requires mean average of ensemble, which we take from equation 2, which was this, if you remember, xi square n is equal to 1 upon summation over I to I is equal to 1 to n xi square n. Substituting 5 in 6, that is to say this opened out equation into 6, which is here. So basically we are taking the right hand side and putting it inside the summation sign, we get this term here. And but we can show that, so we had already shown that delta average is equal to 0. Now we say 2 delta xi n minus 1 tends to 0. Why do I say this? Again the same thing, we are multiplying xn n minus 1 could be 0 and or plus 1, and delta could be minus 1. It could be the other way around, it could be, so I haven't added the zeros here, which I assume to be obvious. So we can, let's add them here, 0 into 1, 1 into 0, also 0, also 0. All of these therefore sum to 0. You want to take an average, you have to sum and divide by the total number, the answer still remains 0, right. So as a result we can ignore that and we say that this sum 1 by n into summation I to sigma of 2 plus minus delta into xi n minus 1 is equal to 0. Therefore xi square n is equal to xi square n minus 1 plus delta square. X square of the 0th position, 0th step is 0 because there is no motion yet. The first step is delta square, the second step is 2 delta square, third step is 3 delta square. In other words, it is xi square n is equal to n delta square. By the rule that we have n t of t is equal to n times tau, meaning to say total time is equal to the number of steps into the time interval between each step tau, then therefore we can say that n is equal to t times tau. But since xi square n averaged is equal to t by tau into delta square, with delta square and tau as constants, by definition the new constant becomes d is equal to capital D is equal to delta square by 2 tau. Substituting in 8, So, by the way, this I have defined as a new term. Yeah, this is a new term. This is nothing but something that we have heard of earlier, which is called the diffusion coefficient, right. And substituting this into 8 will give us delta square by tau, but where is the 2? So, we multiply and divide by 2 and we then substitute and we get x square is equal to x square n averaged is equal to 2 dt. D depends on particle size and the nature of the medium. Now, this is an important equation because this tells us that while on an average nothing happens, motion does not go anywhere, the mean squared displacement indeed has a nature of spread which depends on time. So, it depends on how long you observe for, like we saw with the glass, it took some time to move, and the diffusion coefficient, which itself depends on particle size and the nature of the medium. Typical values of diffusion coefficient for biologically interesting molecules, for small molecules 10 to the power minus 5 centimeters per second, and protein macromolecules 10 to the power minus 6 centimeters square per second. I have also converted these into micron square per second for you, 10 to the 1000 and 100 micron square per second respectively for small molecules and proteins. So, I will stop here and we will continue with the next segment.